Hi everyone, welcome to this new video on G2CPU. This video is going to be a little bit different. It's going to be the first of several parts on the G2CPU performance demo. The G2CPU performance demo is a free and open source application which you can use to profile your system and check what performance benefits you could gain from GPU computing versus standard CPU computing. Now, to get the G2CPU performance demo, you can just go to GitHub and search for the G2CPU performance demo. Once you get into this repository, you're going to find the source code as well as several executable folders. Now, these executables are quite special. They are compiled in such a way that they won't need any G2CPU license. So you can use them freely to verify system performance of potential systems. All you need is, well, the drivers installed, the LabVIEW runtime, and a TDMS file which is compliant with this demo. More on that shortly. So if we scroll down a little bit further, we're going to see the README. And here you will find the TDMS file to download. You can just tap here and it will download to your downloads folder. You can leave it there, put it potentially in other locations. But the main thing on this TDMS file is it's been reconfigured to work with asynchronous reading of TDMS files. So we're going to see some amazing performance, up to 6-7 gigabytes per second from an SSD. Now, like I said, there are also some executables available. Here we have the performance demo executable, or we also have a TDMS converter, so if you make your own TDMS file to run with this demo, more on that in upcoming videos, you can use that executable as well. Besides the TDMS file and of course the executable itself, you're going to need to make sure that all drivers are installed. First of all, we need ArrayFire 3.9. We're going to need CUDA 12.2. Now this is important. ArrayFire 3.9 is compatible with 12.2. Newer versions are in the works, which are compatible with 12.4, but they're not yet released. So for now, let's stick with 12.2. And then beside that, of course, we're going to need the LabVIEW 2024 64-bit runtime. For the rest, in this README file, we're going to have some more descriptions on what each part does. Now, let's say we want to download this. We can easily go to the top right, code, and say download zip file. If you want to fork this code, if you want to just use Git to download it, that's all possible as well. For now, we just quickly used zip. Now you've downloaded both the TDMS file and the executables or the source code. We can navigate to the folder of the repository, and we can navigate all the way down to G2CPU Performance Demo EXE. This folder contains the executable. Now to launch the executable, all we have to do is double tap, give it a second to launch. We can put the actor monitor aside. This is just part of the underlying source code, and we're going to see this UI in front of us. Now, before we start with loading in the TDMS file, we're going to already see a couple of different regions in our UI. Here on top, we're going to see everything based on the TDMS file. So we can load the file. We can even tell it to continuously load the file asynchronously at really high speeds. We have a graph which tells the disk read rate. This can be up to 7 gigabytes per second without any issue. And in this text field, we're going to see a bit more information on the TDMS file. Now in the field below, we're going to see an FFT of the TDMS file. The top one is going to be the GPU FFT, while the bottom one is the same FFT but done on the CPU. And we're going to have a look at some of the parameters. We're going to see that the elapsed time, the time it takes to churn through the TDMS file, is going to differ quite drastically. And we're going to see that our throughput is also going to be quite drastically different. So the throughput here is sending the data from memory to the GPU, doing our calculations, changing to decibels, doing some additional operations on top of that, and then sending it back from the GPU to the CPU. That entire chain That's going to be our metric for the throughput. For the CPU FFT, we're going to have the same thing, but here the throughput is just purely based on the FFT calculation and changing the array to decibels. Now, when we look here to the left, we're going to see the FFT speedup, which is going to compare the FFT calculation time between the GPU and the CPU. And we're going to see the throughput speedup, which is the difference between the CPU and the GPU throughputs in our system. Now, if we go a little bit down in the field below, we're going to see a couple of metrics. So first of all, here we have continuous GPU and a run button, which allows us to manually trigger an extra GPU run after one has been done, or with continuous GPU tell it to continuously do the calculations. Below that, we're going to have the CPU to backend data rate, so that's how fast we can get data from our RAM memory into the GPU. We're going to have our backend to CPU data rate, which is how fast we can get data from the GPU to the CPU. And beside that, we're going to have the GPU FFT calculation time. This is the time it takes to calculate a single FFT. Now, how big are these FFTs? Well, for now, we're going to stick to an FFT of 1 million data points. Beside that, we also have the GPU batch size. So GPUs like a lot of data. And with this, we're actually going to do multiple FFTs with the same function call. We're going to see that in the upcoming video where we're going to dive into the codes. But for now, we can just tell the system, hey, I have multiple FFTs for you. Can you calculate them in one go? Which is going to drastically improve our system efficiency. Now, while we have this for the GPU, we also have this for the CPU. Here there are a couple metrics, but a lot less. Again, we have the continuous CPU and run, so we can tell it, hey, also continuously run on the CPU. And we're going to have the FFT calculation time. This is how long it takes for the CPU to do this calculation. Now, to run this demo, all we need to do is go here on top and click Load File. Then we navigate to the TDMS file we just downloaded. And we say, hey, launch. Now, the first time that you are going to launch this, you're going to notice, well, the GPU is taking a bit longer or it can lag for a couple of 100 milliseconds. This is just because all the DLLs need to be loaded in, all the kernels need to be loaded into the GPU. But after that, it goes a lot quicker. Now, if we look here, well, we were able to read the disk at 6.5 gigabytes per second. Our TDMS file, well, here you can see where it was located, the group and the channel that was used, and the amount of samples that were present in the TDMS file. Here we can also see how quickly the GPU was able to calculate all the FFTs on this TDMS file, as well as the throughput or the average throughput of getting data from RAM back to RAM after the calculation has been done. Below that, we have the CPU FFT. Here we can see, well, that's quite a big difference. It took 7.1 seconds to do all these calculations with a throughput of 29 megasamples a second. Please keep in mind this is a 1 million point FFT. Overall, on this first run, we're going to see, well, the FFT speedup was about 100 times. So the time it took for the GPU to do the calculations versus the CPU, and our throughput was about 27 times faster. So what does that mean? Well, our FFT was calculated in 200 microseconds or 0.2 milliseconds, while our CPU took about 20 milliseconds to do the same calculation. Now, one thing with the GPU is it likes to run continuously. So what we can do is say, hey, enable continuous GPU, and let's run it now. And we're going to see our performance suddenly boosted. This is because the GPU has the same code in memory time and time and time again. It doesn't have to lose that efficiency in reloading systems into its memory or reloading code into its memory. And we're going to see our throughputs went up from 750 megasamples a second to between 800 and 1,000 megasamples a second. This is on my laptop, on a 4080 laptop GPU. And you can see also the elapsed time dropped from 0.5 seconds to 0.3 seconds or 0.35 seconds. We can also see our GPU FFT calculation time dropped to about an average of 0.16 milliseconds. And this gives us a throughput speed up of about 33 times, while the FFT calculation itself has been sped up by almost, or just about 120 times. So this GPU is able to calculate the FFTs at 120 times faster than a CPU. Now, how can we boost this even further? Well, keep in mind, we are doing our calculations on the GPU, but throughput is the sum of, in this demo, is the sum of sending data from RAM memory to the GPU, then on the GPU doing the calculations, and then getting the results back from our calculations. So the way that we can optimize this throughput is by saying, hey, let's reduce the amount of data we're getting back. So let's say you have peak finding and you're searching for a specific peak or a specific range. Well, what you can do is, well, we can zoom in, for example, on the GPU and tell the GPU only send back the data we're interested in. Now, for the sake of this demo, this is done completely manual, but nothing is stopping you from creating your own peak finding algorithm to search for regions of interest, which you can then bring back in their entirety without taking the entire data set. Now, the way that we can do this is, well, first of all, let's fill in some parameters saying, hey, we want a frequency width of 200 Hertz. And now we're going to say, hey, override zoom, so telling the system, hey, let's zoom in. Let's fully enjoy that RBW of 250 millihertz. And what we can see now is suddenly our throughput has jumped up from 900,000 megasamples a second to 1,300 to even 1,500 megasamples a second, which boils down to a throughput speed up of 50 times compared to the CPU. So remember, the CPU is running at 29, or is giving a throughput of 29 megasamples a second. That's an amazing difference with just this demo application. Now, we can also run the CPU at the same time. What we're going to see is, well, throughput goes down a little bit just because we're using the same RAM memory, so they're competing a little bit with each other. But still, we're going to see this throughput of 48 to 50 times, which is great. Even we can put here the zoom, and still we're going to have this great throughput. And also, as you can see here quite clearly, this graph is updating quite nicely while the CPU is lagging, just because the calculations aren't coming in that quickly. Now, one of the last things that you can also play with is the continuous disk. So what we can do is enable this, reload our file, and what you're going to see is in the background, the demo will continuously load in this demo file. We can quickly clear the charts to see the most up-to-date data. And as you can see here, we're constantly loading in data at about between 5 and 6.5 gigabytes per second. Now, please keep in mind, this is time it takes to this is based on the time it takes to load in the file. So if you would look at Task Manager, you will see that the perceived performance is a lot smaller. This is just simply due to the Task Manager using the average data rate per second rather than looking at the maximum data rate at any given time. Now, I hope you found this video interesting. Stay tuned for the next part coming up really soon, where we're going to dive into the actual source codes. In the meantime, if you have any requests for upcoming tips and tricks videos, feel free to reach out at info@g2cpu.com or just put it down in the comments. And of course, if you like these types of videos, please subscribe. And well, thank you very much. Have a great day. Bye!